Section 3.13 Internal energy, enthalpy, and specific heat of ideal gases. In this section, we are going to introduce ideal gas relations on internal energy, enthalpy, and specific heat. Ideal gases follow PV equals RT. So P is the absolute pressure. V, lowercase v, is the specific volume. R is a gas constant. T, temperature in absolute scale. So Kelvin or Rankine. So there are several relations in this box, and the relations can be applied to ideal gases. The specific internal energy is a function of temperature only. That means at a given temperature, the specific internal energy can be determined. The relation between the internal energy and temperature can be found from the definition of constant volume specific heat. So from the definition of specific heat, du equals Cv dt. So integrate both sides of the equations. The change in internal energy is the integrations of Cv from the initial temperature T1 to final temperature T2. Let's see the process on a PV diagram. Y-axis is going to be pressure, x-axis specific volume. So constant temperature line will be like this for ideal gases. Let's say this is T1. At T2, constant temperature line will be like this. Initial state is at temperature T1. The final state is at temperature T2. And let's say this is 2A. And another state at temperature T2 is 2B. Temperature is still T2, but the pressure is different. Another state at T2 at different pressure, 2C. So we have three different processes. This is process A, process B, process C. So process A is a constant volume process. The internal energy at state 1 is U1. The internal energy at state 2A is U2. So the internal energy change for process A is U2 minus U1. Now take a look at process B. First of all, it's not a constant volume process. The internal energy at state 1 is U1. The internal energy at state 2B is still U2. Since the internal energy is a function of temperature only, so temperature at state 2B is T2. So the internal energy change for process B is U2 minus U1. And we will get the same result for process C. Since the internal energy at state 2C is also U2, internal energy change for process C is U2 minus U1. So the internal energy at any state on the constant temperature line or T1 is constant, U1. The internal energy at any state on constant temperature line or T2 is constant, U2. So since the internal energy and constant volume specific heats are only function of temperature, the change in internal energy between the two temperatures is independent of the process. Similarly, enthalpy also depends on temperature only for ideal gases. From the definition of specific enthalpy, dH equals Cp dt. So by integrating Cp from T1 to T2, enthalpy change can be expressed as this. The enthalpy H is defined as the sum of internal energy and PV. For ideal gas, H is U plus RT. U is a function of temperature, R is constant, T temperature. So H is also function of temperature only. If the temperature remains constant during a process, there is no change in enthalpy. An important relation between the constant pressure specific heat and constant volume specific heat can be found from the definition of enthalpy. So differentiate the equations with respect to temperature. dH equals du plus R dt. Divide the equations by dt. dH over dt, du over dt plus R. dH over dt is Cp, du over dt is Cv. So we developed a relation. Cp equals Cv plus R, or the difference between Cp minus Cv equals R. The specific heat ratio is defined as K. K equals Cp over Cv. And Cp is expressed as Kr over K minus 1. Cv is also expressed as R over K minus 1. So these equations is based on these two relations. The specific heat is a function of temperature. Figure 3.13 shows how the constant pressure specific heat changes with temperature. So it increases with temperature, but the specific heat for monatomic gases such as argon, neon, and helium remain constant. And the variations of specific heat for other gases is not large, especially within the small temperature change during a process. So we typically assume the specific heat is constant during a process and take the average specific heat in a certain temperature range. Section 3.14, applying the energy balance using ideal gas tables, constant specific heat, and software. We are going to evaluate internal energy and enthalpy of a substance and apply the energy balance for a system containing an ideal gas. There are three different methods to evaluate the properties of an ideal gas. So first, use the thermodynamic tables. Second, use the constant specific heat. And third, use softwares. But we are not going to cover the method using softwares. Let's see the first method using ideal gas tables. The property tables for ideal gases are available. Table 8.22 and 8.23 include ideal gas properties for common gases, such as air, carbon dioxide, carbon monoxide, water vapor, oxygen, and nitrogen. So those gases are considered as an ideal gas. So property tables provide the accurate thermodynamic property data. So if the property tables are available, use them. So it will provide the most accurate data. So let's solve the following question using ideal gas tables. Example 3.9. A piston cylinder assembly contains 2 pounds of air at a temperature of 540 degree Rankine and a pressure of 1 atm. The air is compressed to a state where the temperature is 840 degree Rankine and the pressure is 6 atm. During the compression, there is a heat transfer from the air to the surroundings equals to 20 BTU. Using the ideal gas model for air, determine the work during the process in BTU. So at state 1, so initially we had temperature 540 degree Rankine and pressure 1 atm. At state 2, temperature is 840 degree Rankine. Pressure is 6 atm. So any simple compressible system, two independent intensive property fix the state. But we have an air which can be modeled as an ideal gas. So internal energy and enthalpy are only function of temperature. And during the compression, there is a heat transfer from the air to the surrounding. So heat is lost to the surrounding. Q is negative 20 BTU. Since heat transfer from the air from the system to the surrounding. So we are going to apply the energy balance to determine the work during the process. So energy balance Q minus W equals delta E. Delta E is sum of kinetic energy change, potential energy change of the system, plus internal energy change. And assume that system is stationary, kinetic energy, potential energy cancelled out. And we need to determine the work during the process. So write the equations for work. Q minus delta U. The uppercase U denotes the extensive property. So Q minus, so mass times specific internal energy change. Q is negative 20 BTU. Mass of the air is 2 pounds. And we need to determine U2 minus U1. So the internal energy is only function of temperature. So at state 2, temperature 840 degree Rankine. The internal energy at this temperature is 140, 398 BTU per pound. And U1 at state 1, temperature 540 degree Rankine. Internal energy is 92.04 BTU per pound. So W is negative 123.9 BTU. So the negative sign indicates the work is done on the system. So note that we didn't use the pressure to calculate the internal energy change, since the specific internal energy for ideal gases only depend on temperature. Let's take a look at the second method. We're going to take specific heat as constants, and this is an approximation of specific heat. So actually the specific heats are dependent on temperature. But by assuming that the specific heats are constant, the analysis will be simplified. From the definitions of constant volume specific heat, we can find the relation between the enthalpy and temperature. Constant volume specific heat is defined du over dt at constant volume. The internal energy of an ideal gas is a function of temperature only, so the partial derivative becomes the ordinary derivative, du over dt. So we can say that constant volume specific heat, or CV, is dependent on temperature only for ideal gases. So du can be written CV times dt. Assuming CV is constant and integrate CV from T1 to T2. So U2 minus U1 integration from T1 to T2 CV dt. Since CV is constant, we can write CV times T2 minus T1. So note that CV is a constant, and this is the internal energy change for ideal gases. Likewise, we define the constant pressure specific heat, Cp dH over dt at constant pressure. And for ideal gas, enthalpy is only function of temperature only. So we can write dH over dt. So dH equals Cp times dt. On integrations, H2 minus H1, Cp times T2 minus T1. So let's see the following questions to evaluate the internal energy change using the constant specific heat. Example 310. Two tanks are connected by a valve. One tank contains 2 kg of carbon monoxide gas at 77 degrees Celsius and 0.7 bar. The other tank holds 8 kg of the same gas at 27 degrees Celsius and 1.2 bar. The valve is opened and the gases are allowed to mix while receiving energy by heat transfer from the surroundings. The final equilibrium temperature is 42 degrees Celsius. Using the ideal gas model with constant specific heat, determine the final equilibrium pressure in bar and the heat transfer for the process in kilojoule. So we have two separate tanks. Tank 1, pressure is given, temperature is given, mass is given, volume is unknown. In tank 2, pressure is given, temperature is given, mass is given, volume is unknown. Carbon monoxide can be modeled as an ideal gas, so it follows PV equals MRT, ideal gas law. So we can solve it for volume, MRT over P. So we can determine the volume of each tank. And the final equilibrium pressure, P, let's say sub F, final state, can be determined M total R T final over volume, total volume. We know the total mass and gas constant are remain the same. Temperature at the final state is given 42 degrees Celsius and the total volume can be calculated. And we also need to determine the heat transfer for the process. We apply the energy balance and we solve it for Q. The pressure at the final state, total mass, gas constant, temperature at the final state, and total volumes. So masses of each tank, gas constant, and the final temperature. Total volume is volume 1 plus volume 2. And volume can be solved by the ideal gas law. Cancel out the gas constants. Plug in properties and the values. We get the pressure at the final state. We also need to determine the heat transfer for the process. So apply the energy balance equations. Q minus W equals delta U. And there's no work associated with the process. So W cancels out. And Q equals delta U. And the internal energy change between the initial and the final state. So the internal energy at the final state, total mass times specific internal energy at the final temperature, minus, we are going to subtract by the sum of the internal energy of each system. So system 1 mass times internal energy at system 1 plus mass of the system 2 times internal energy of system 2. So we can rearrange the equations. M1 U final minus U1 plus M2 U final minus U2. Assuming constant specific heat, CV times temperature difference. And constant volume specific heat can be determined from a table 820. So in table 820, carbon monoxide is here, and at 350, CV is 0.746, at 300, 0.744. So there's a very small change between the two temperatures. And the process in our systems changes from 315 to 350. So we can calculate CV at 315 Kelvin. And there are two ways to calculate CV. And first, we take the average of CV at two different temperatures. That's one method. And the second method is to take the average temperature of these two, which is 332.5 Kelvin, and take the CV at 332.5 Kelvin by interpolating the values between these two. And we plug in the properties and the values. So we got the positive 37.25 kilojoule, which means heat is supplied to the system. Section 3.15, Polytropic Process Relations. So we are already familiar with the polytropic process, and polytropic process is expressed as the product of pressure and volume to the nth power is constant. N is the polytropic index, it is a constant. Polytropic means taking various courses of action or versatile. Depending on the polytropic index, it takes a variety of paths. When N is 0, it represents a constant pressure process. As N approaches infinity, it represents a constant volume process. When n is equal to 1, the pressure is inversely proportional to the volume. So from the polytropic process between the two states, boundary work can be determined from this relation. So when the exponent n is not 1, the boundary work is here. And when the exponent is 1, the boundary work is expressed here. If an ideal gas follows a polytropic process, it must satisfy both the ideal gas law and the polytropic equations. And these relations were derived from the ideal gas law in conjunction with the polytropic relations. Example 3.12. Air undergoes a polytropic compression in a piston cylinder assembly from pressure 1 atm, temperature 1 70 degree Fahrenheit to pressure 2 5 atm, employing the ideal gas model with constant specific heat ratio K, determine the work and the heat transfer per unit mass in BTU per pound. If N, the polytropic index, is 1.3, B, N is K. Evaluate K at temperature 1. So at state 1, pressure is given, temperature is given. At state 2, pressure is given, temperature is unknown. And we have air in the system. Air is considered as an ideal gas, and it undergoes a polytropic process. So we are going to use the polytropic processes relations as an ideal gas. So ideal gases that follows the polytropic process and we solve it for T2. And the work during the process. So we plug in the values. Universal gas constant for air. Divide by the molecular weight of air. Applying the energy balance equations. Assume the system is stationary, kinetic energy, potential energy cancels out. And assume that the specific heat is constant. To determine the specific heat ratio K, see table 820E. We evaluate the specific heat ratio K at 70 degree Fahrenheit, which is given in the problem statement. At 70 degree Fahrenheit, K is 1.401 BTU per pound degree Rankine. For ideal gas law, CV is R over K minus 1. And we solve it for Q. And lastly, determine the work and heat transfer per unit mass when N is equal to K. Plus CV. R over K minus 1 times temperature difference. So this is equals to 0. So the exponent n equals K. There is no heat transfer during the process, and the work is done on the system.